component, you have 1 minute to charge the reporter.
We would like to challenge problem number 14 for our membrane.
Okay, so reporter 14. Okay, time is up.
We accept.
Okay, so the report accept the challenge problem number 14 for our membrane. And please write down your name on the board. And so the report is 5 minutes to prepare. So all the 3 teams at the end of the fight, please give the green sheet to the assistant. Okay, time is up. And in total you have 12 minutes to begin.
Honorable jury, fellow competitors, this is a reporter from Team Excelsior, reporting problem number 14, ball on membrane. When dropping a metal ball on rubber membrane stretched over a plastic cup, a sound can be heard. Explain the origin of this sound and explore how its characteristics depend on relevant parameters, and mainly focusing on investigate the origin of the sound and how the different parameters affect the characteristics of the sound. First, I'll start with a preliminary experiment about the observation video about the rebouncing of metal ball, and we have qualitative explanation about the origin of the sound. Our theory includes wave equation, boundary condition, and basal function. And our experiment's parameters include landing position, elongation, and radius of the cup. First, for the preliminary experiment. From the observation video, we can see that every time it has the rebouncing height decreases. It is because the collision of the membrane and causes the energy to lose. And when we investigate the sound, we can see that there are specific peaks that looks like this, and every rebouncing. So basically, the phenomenon when a metal ball drops on a membrane, it causes the membrane to vibrate, which causes the air particles inside and outside it to vibrate, and causes the resonance of the sound that we heard. And this kind of dynamic keeps repeatedly conducts. And first, I'll talk about our theory about the wave equation. First, when we change the xy plane coordinate of the wave equation into a polar coordinate, we can get we separate the product into three parts, which would be related with R of R, H of theta, and T of E. And when we input the value of U inside, we can get this part equals to negative m squared, which m equals to 0, 1, 2, etc. And we can note that the value of H and T. And when we input the value of H and T, we can know that the answer of this function it fits with the basal equation, and the basal equation should be the answer of basal function. And this is the basal equation diagram. And our boundary condition sets the edge of the circular plane would be 0. And in this part, the Jm of rho mn equals 0 too, since it hits the 0 on these parts. By calculating, we can know that this is a relation between Kmn and rho mn, and also the frequency and wave speed and basal function. And we can also know the magnitude of rho 01 or rho 11, rho 02, etc. This is a simulation of J02 and J21. So when a metal ball hits on the center part of the membrane, it causes the wave like this. And when we look at, instead of three dimension, we look at in 2 dimension, the cross section will look like this, which fits with the J02 function. And when it hits on the edge, it might cause 4 corners to vibrate. And when we look into 2 dimension, it looks like this, and it fits with the J21 function. In order to prove that the basal function does exist in our experiment, we use a signal amplifier and a sound speaker to prove that the resonance does exist and causes this J1 function in our experiment. And in this part, we can see that when it's about 365 Hz, it causes the four corner to vibrate, which fits with the J21 in our experiment. So first of all, in our experiment, we believe that the tension and aerial density is an important factor to influence the wave speed. So therefore, this is the method that we measure the tension of membrane. First, we pull the one side of the membrane and we calculate the tension of it. And this is a relation between the tension of membrane and the elongation. And for the aerial density part, and this is a relation between aerial density and elongation. These are equipments that we'll be using in our experiment. First, a square membrane and a directivity microphone, electromagnet, metal bowl, and plastic cups. This is our experimental setup. First, we use electromagnet to control the releasing height, and which we control the releasing height as 15 centimeters from the membrane. And then we use acrylic cover and also a directivity microphone to ensure the accuracy of the receiving of the sound. And last, for the membrane part, there are actually circular dots on it to make sure the landing position. So for our first experiment about the landing position, we define the radius from the center of the membrane to the landing position, which we change it from 0, 1, 2, 3, and 0 means that it hits on the center part of the membrane. And we are measuring for the frequency, and these are the control variables. This is a result that for when we hit in the center, and we can know from the basal function we already know that, for example, rho 01 equals to 2.404, and when we bring it and we calculate the wave speed by audacity, and we can know the wave speed, and we bring into this equation, and we can know that the rho 01 and the wave speed, and we can know the specific places that of the frequency, F01, F11, and F21, etc. And when we overlay all the charts together, we can see that it doesn't affect the places that appears with the specific piece. And when we look closer to this one, we can see that the aerial density of the intensity changes, and it is because that in basal function, when it heads to the middle part, it causes a bigger vibration, which causes a greater intensity. And so it should look like this. And when we change the elongation of the circular, which we define as the distance between two dots that on the circular plane. And we're also measuring for the frequency in this experiment, and these are the control variables. So when we look closer, we can see that actually, because the elongation changes, and it causes the wave speed to increase, which makes the graph to go rightward. And this is a relation between the wave speed and the frequency in our experiment of elongation. For the next experiment about the radius of the cup, we changed the big R, the capital R that we define as from the center to the edge of the cup, and we change it. These are the radius that we changed, and we measure the frequency also, and these are the control variables. In this experiment, you can see that because it has negative correlation or with the with the capital R, so therefore the track will go leftward. So the frequency goes leftward. And this is a relation of frequency and how radius changes, radius of the size of cup. And about the collision interval, and this is an observation video, we want to find out we want to investigate how the collision interval is affected and the sound interval. So this is a qualitative explanation about the tension, how it affects. So in this part, when the elongation is bigger, it has greater tension. So the force of F2 is greater than F1. So it causes a larger component force that goes up and makes it to rebalance. And therefore, the coefficient of restitution and the elongation relation looks like this. And for the discussion part, I want to discuss about ear resonance. During our experiment investigation, there are some peaks, specific peaks that we cannot explain by our basal function. However, when we look closer, we could know that it is about 2 times of the 337 hertz. And this is appearing at the 674 hertz, which by this equation, we think that it comes from the ear resonance, since we are not measuring the vibration of the membrane. We are measuring the ear resonance. We are measuring the sound that comes from the ear. So it causes the ear resonance, and we believe that is the multiplication of frequency because it appears in about 2 times of this one. And for the deformation part that we want to discuss is about, in this slow motion, you can see that it does cause deformation. However, because that we measure we minimize the mass of the bolt and the height that we release. So therefore, we can minimize the deformation in our experiment. And in this part, the original elongation is way bigger than the colliding deformation that is caused by the collision. In conclusion, when the laying position of the circular membrane changes, the intensity decreases because it is farther from the center. From basal function, you can see that if it's closer to the center, it will cause a bigger vibration, which will cause greater intensity. So therefore, the chart should look like this. It decreases. And for the elongation of circular membrane, we can know that because the capital R has a negative correlation with the frequency. So therefore, when we increase because the wave speed is affected by the tension and also the aerial density. So when we increase the wave speed by the tension, because the elongation increases. So in this part, the V is greater, so which causes the Fmn because it has proportion with wave speed. So this chart it goes greater. And for the radius of cup for the circular plane, we change the capital R in this part. And because that it has negative correlation with the frequency, so therefore the chart will decrease because we are increasing the capital R, which is the size of the cup. And thank you.
Okay. So, Paula, you have time to question the reporter in 2 minutes.
Okay, so let's start with the origin of the sound. So do you believe that the origin of the sound is on the membrane, or like when it's does the sound happen when the ball is still on the membrane, or when it actually leaves the membrane?
It both happens.
It both happens. Okay, and the next question is, so the original sound is because of vibration of membrane, is that correct?
Yes, and it causes the air particle to vibrate, and the resonance is the sound that we heard.
Oh, okay, no problem. And then the next question, I would like to ask you, can you turn to page 26? So I just want to make sure, like, how is the tension is attached to the cup, right? No,
Yeah, we use rubber band to stick. We use rubber band to make it to stretch, and it's controlled on the cup.
And you control the tension by measuring the distance between the dots?
It helps us to compare. So, and this part is either, because the original is 0.5 centimeters, and so it helps us to control the illumination of the circular plane.
Okay, no problem. Then can you turn to your page where you have like the frequency one? Yeah, this one. So how would you define like how would you define if a peak is big enough for you to like despair? Because you see, like there's actually really other small, really close. So I wanted like to know like how you define what is big.
So from the basal function part, you can know that when it's sorry.
Please. enter.
So when it's closer to the center, it has a greater, the biggest peak should be J0. That comes from the J0.
So you're trying to fit the theory. So you try to see if the theory would imply to your experimental data, and that's how you get the frequency.
We know that the exactly place that where row 01 is hit. So when we
Okay,
insert,
the opponent you have to need to prepare. Okay, time is up, and the opponent you have 4 minutes.
Okay, so today I'm studying the continuum, and today I'll be focusing on question number 14, ball on membrane. So first, we'll talk about the problem statement, where the problem statement asks us to, where the problem statement asks us to drop a metal ball on the membrane and then investigate the origin of the sound and also the characteristics of it. So in the reporter's report, we can see that the characteristics of the sound they investigated was mainly the frequency of the sound, though they did add some volume when it reaches their conclusion. And then the theory they used were Basel equations, and then also they stated that the origin of sound was caused by the vibration of the membrane and then causing the air particles to also vibrate. And then they also found in their experiment that so the frequency is related to the tension and the radius of the cup, and then also how and also where the dropping part is. So so we're going to talk about the pros of the report is that they clearly explain the circular membrane background. which we assume that they later on put it into the use of phasal equation. And then the next is they provide theory which matches up the experiment and setup and result. And then they analyze the sound and fix the unexplainable peak with air resonance. However, they lack the explanation of multiple bouncings, which might trigger complex bouncing mode. And then they also lack the consideration of the depth of the container, as they stated right here, where they say with air resistance and higher harmonics would happen. We think that the height of the cup would actually change the effects of the experiment. However, when they're talking about this particular the radius parameters, they did not talk about if they had the height of the cups same, if I remember correctly. And then also they did not explain the reason for choosing several specific equations, which we're also going to talk about later. And then so the points to be discussed were, so basically we're going to clarify some points, such as the origin of the sound, which is where and when did the sound happen? Did the sound originated from the membrane itself? Where exactly did the air, which the reporter said might vibrate with the most and then would result in the sound that we hear? And also we should how to distinguish different sounds, like such as the layering of sound, which may cause by different bouncings. And then also theory. We're also going to talk about the position of the ball dropping, and then also talk about like different modes happening in a single jump. I'm not quite sure about that. I'm not clarified about that part, so I'm going to discuss it later. And then the next would be the data extracting, where I pointed out in the short questions where they have different peaks, but however, they did not exactly tell me how they get the frequency that they want. And from his answer, I assume that for now that they might have fitted their theory into the experimental data, instead of like looking at the experimental data and then see if it fits the result, if it fits the theory. And then I would like to move on into the discussion part.
Okay, let's go through the next part.
Okay, so first, I think I just asked if can we, so for the original sounds, would you say that the air vibration is a cause in the inside the cup,
It's
or
mostly outside the cup that we heard.
it's mostly the outside of cup?
But the inside cup affects the resonance.
Oh, okay. So so it's mainly vibrating the open air,
Yes.
but there's also air vibrating inside the cup, which causes the resonance. And so, are you expecting a decrease in volume for the higher harmonics frequency?
We did not investigate about this part, how we did not do this parameter. However, I believe that it will cause the tune to be different, since you have a different resonance area of the air particles.
Okay, then talking about air resonance, so we all know that the higher frequency, higher harmonics is related to the length of the container, right?
Yes.
So did you, for your experiment, during your experiment of changing the radius of the cup, did you also keep the radius?
Yes, I keep the height the same. Well, we changed the radius of the cup.
Okay, so that's reasonable. And now moving on, can you explain why you chose to use the Basel equation?
Basal function.
Yeah, Basel function. I'm sorry.
So, please review the basal function chart. Yeah. So, this is now use the blackboard. Now you use the blackboard.
Okay, yeah.
So basically, basal equations is the dynamic when you look from the membrane, and when we look from the center, and you can see that when we look into this part, and you can see how it vibrates. For example, so this is how the basal equation is describing about the vibration of the membrane.
Okay, so if today we were supposed to use like such as a squared container, would you say that we can still use the Basel function?
You mean square? Please turn to the backup page. We did conduct experiments about the square membranes and how. Backup page. So this is our because that the boundary condition is different. So when we set these part into 0, you can find out that when you are using square membrane to conduct an experiment, it confirms like a sine wave instead of Basel equation.
Sorry, can you repeat your sentence again?
Because the boundary condition is different from circular membrane. So after calculating, and when you bring into the number into the wave equation, so you can see that it converts to the sine wave when you are conducting with a square membrane.
Okay, so if that's so, would they also affect the symmetrical, like the symmetry, like the geometric of the bouncing? Because we all know that from your.
Yeah, it looks like a sine wave, and however, in Basel function, it doesn't, like when you are using square membrane, it looks like a sine wave when it's bouncing.
So you're saying that it would feel like the whole, completely same when you're using square, right?
It's a symmetrical, if you are describing about that.
Well, the whole system would still look the same, even if you use a different shape membrane. Is that correct?
Which do you mean the whole system? Like
For
which
example,
part do you
like
mean?
the vibrating part and then all frequencies would all be the same.
It will not look the same when you are changing the shape. The wave will not look the same.
Oh, okay, no problem. And then moving on into the next question, can we go to the data? Can you go into the table where you have wave function?
Wave function.
Yeah, wave function. So
This part?
the other, I think it's yeah, page 12. So can I ask how do you know like in terms of the answer of like differential wave function?
So when in this part we change this into a polar coordinate. So we can get that the product U is separated into 3 parts, which is related to R of R and H of theta and T of T. And when we get the U, we can input back into the wave equation, and then we can solve this function of the equation.
So we have to separate all of the variables, right?
Yes.
Okay, then that's good. Then I would like to ask you about some data extracting methods. So
About the frequency part.
yeah. So can you please tell me what method you use to get the graph that you have right here?
So we use it by fast Fourier transform.
Oh, okay. So can you briefly explain to me what that is, just to make sure.
So first, we know that, as we mentioned in Basel function, first I'll talk about the experiment data. So this would be the greatest peak and the second greatest. And when we look into, in our theory, we can know that the greatest peak comes from the row 0, 1.
So you know it by theory, and so you did not look at. So instead of looking at this peak to see if it's theory, you use the theory to check if the frequency has a peak.
We use our theory because we know that, for example, row 0, 1 equals to 2.404. And when we input the number and also the wave speed of this tension of membrane, and we can know that the exactly frequency.
So are you able to conduct like how low 0, 1 is in like experiment?
No, it will not change.
It will not change. So
Yeah, because in Basel
prove
function, it will never change because that's the answer of the Basel function. The situation, the position of row 0, 1, row 1, 1, row 2, 1 will not change.
Okay, then can I also ask like exactly what start is this data extracted? What time frame is this data extracted?
Because that it will cause deformation, right?
Yeah.
So because that it will cause deformation when this sound happens. So we conducted we measured the sound that when it released from the ball, from the membrane.
So you said that before that you believe that the sound would both happen when the ball hits the membrane and also bounce off the membrane.
Yes.
Right?
So we measured the sound that when it's bounced off the membrane, so it won't cause deviation.
I'm hardly. Can you explain? I'm not really quite sure why you only chose to use the when it's bouncing off instead of like also touching it. Since you both said that there should be that they should both be like providing sound.
It will sound the same, but it's idealized, it will sound the same. But however, because in this part there will cause deviation, so the wave speed might change. So we choose a part when it's releasing from the ball, and when it's like rebounds from the membrane.
So just to make sure, do you have? I'm still kind of sure. Did you actually like compare the experimental data with the that to ensure that it's all the same?
Mostly it's the same, but there are some deviations that we think might cause by the deformation.
Oh, okay, no problem. And then also, I would also like to ask, like, so we're talking about higher harmonics before, right? So if there is like standing waves with the air, right?
Yes.
Then do you think that is caused by that
You mean a harmonic?
yeah, it's also conducted by so it should be the air that's actually vibrating, right? Then do you think in that case the higher harmonics can still fit into when what you use, since you're calculating the vibration of the membrane, however the higher harmonics should be vibrating the air?
I'm not sure about the harmonic that you're talking about, and however, may I use a black word again?
Sure.
So however, when the membrane, when we're in reality, when the ball hits the membrane, it causes deformation, right? So it will not have only one contact point. So in this part, it will have contact points. And in reality, we cannot hit the exactly central part of the membrane. So it will, in basal function, when it hits, please do the basal function part. When it hits exactly in the J01, and when in the center, it will only cause the J0 function. And however, in reality, maybe it might drop on this part or this part, so it will cause different kinds of
yeah. So what
waves.
I'm asking about is
So the harmonic comes from the overlaying of different kinds of waves and basal function.
Oh, so there is the overlaying of sounds which is conducted by.
Yes, and we use fast Fourier transformation to get the J01 and J11 and other kinds of functions.
Oh, okay. And I think that is our time. Thank you.
Thank you.
Okay. So the panel have 1 minute to summarize your discussions.
Okay, so basically in our discussions, we described about different parts, especially the origin of the sound, which we both agree that the vibration of the membrane would cause both the air and the open air to vibrate, which causes the sound, and while the air in the cup would also create higher harmonics. However, so we also talked about like how higher harmonics is conducted. However, I still believe that because the higher harmonics is caused by the air vibrating instead of the membrane vibrating. So I'm not really quite convinced that we can also use the basal function for the harmonics part, which is also describing the vibration of the membrane. And then so there's also some points that we missed to discuss, such as the parameters which they use, and also is there any more possible parameters. But we also discussed like how also to check on their experimental setup, and that would be my conclusion. Thank you.
Okay. And you have 2 minutes to question.
Please turn your attention mark. So we can there are 4 sides that is connected with the membrane, and we pull one of the side because when the distance between every position of the dots are the same, the illumination should be the same, so have the same tension. So we only pull one side of it and measure the tension. You mean caused by the deformation, so the tension will not be the same? In our experiment, as I mentioned, we did consider that the deformation will cause a different tension. So we use a slow motion to capture this and make sure that it won't affect that much. It affects a little bit, but it affects a little bit, but however, in this part we can note that the origin illumination that gives which is the tension is way bigger than the colliding deformation, so it will not cause that much of the difference of tension. And we control the ball, in our control variables, we control that the releasing height is only 15 centimeters, and the ball is really small and really light, so it will cause the minimum of deformation. Can you rephrase your question?
Okay. You have the reviewer has 2 minutes prepared.
他怎么没洗呀？训练是暂时，我要主要去实习。去工作。Okay, time done.
So the reviewer, you have 4 minutes to present.
Session 14 for our member. This is a common statement. The reporter mark the origin of this sound and how it currently depend on the rhythm's transition. This is a summary of this program. First, they measure the tension of the member, and the member vibration causes the sound. Measuring the vibration of air inside of that of the member. That is question 1. The opponent question is they measure the sound inside or outside cups. The reporter say the difference between different areas of the air. The question 10. The opponent asks, by using vessel function, the reporter says that thinking it matches the phenomenon report. The question sheet 3, the opponent asks the controlling head or not. The opponent says yes. Comments of the reporter. Pros. Their data is clear and they duly experiment based on theory. They explain the association between the theory and the experiment. They did not mention how many times did they do the experiment. Did not consider enough association. And they used two simulated formula in a 3D experiments, and they no clear conclusions, and keep uncertain the tool used for measurements. This is comment of the components. First, they list point clearly and discussing on the important parts of the experiment, but they giving less suggestion. Thank you.
So the reporter, you have 2 minutes to conclude.
I'm going to respell competitors. This is the concluding remarks from the reporter. First of all, in our experiment, we have 2 provings of the basal function, which first is the resonance of the membrane, and the second is that about the misunderstood of the opponent. She thought that we fit the experiment data in our theory. When we investigate about the sound, we can know that probably the F01 comes from the is about 300 hertz, and we found out that when we bring into the value of, for example, rho 01 is 2.404, and when we input the value into this part, and also we know the wave speed by audacity, and when we input, we can find out that the frequency does fit with basal function. And we use basal function because it shows the vibrating of the membrane, as I mentioned on the blackboard. And basal function, these parts, for example, rho 01, rho 11, rho 02, the value of these parts will always be the same. And the square membrane wave is sine wave, which cannot be used in the basal function. For our further experiment we did about the investigating of square plane and how will it change when the boundary condition is different. And we found out that it doesn't fit with basal function. Instead, it fits with the sine wave. And however, we only did about the landing position, and we can know that it has difference peak with the basal function. And in our experiment, we use fast Fourier transform to track our frequency and also use to measure the amplitude. And the deviations that might cause in our experiment can be neglected because we try to minimize the deformation that may cause different tension and different wave speed. And for the reviewer has said about the average taking. We conducted the experiment 5 times and to take average and get error bars. Thank you.
Okay. So we have 5 minutes for you to ask questions.
When you bounce the ball land on different positions.
No,
There are different sound. The ball bouncing at different positions.
it will not cause different sound. It will only cause different intensity from the.
Frequency is the same. This experiment.
When you are changing the landing position, they have the same peak, and so which means that they have the same frequency, and the sound is the same.
Video. Experimental video. Video. Oh, P. Yes. We need to hear the sound. You need to hear the sound. Could you connect this?
So in our experiment, we only took the first sound that we heard. So because after different
Let's create a sound. See, when you land on different position, the frequency is different. Why do they show on your landing different position? You land on different position, have different frequency.
we believe that is because in our experiment we only take the first sound that we heard, but in this part it would be harmony of the sound.
So actually, I believe that by dropping the ball on different positions, it would actually create different modes of the circular membrane bouncing mode. So it might actually affect the frequency that's actually happening to our ears.
But I didn't show you data. Do you think the problem is there?
Yes, I still think it's a problem.
Can I get further explanations?
Let the reviewer answer first.
Okay.
What's your opinion?
The different procedure and the and the function one will be the, so we use the baseline function, we enter one guy, us to be the
So in the spatial function part, so when we conduct our experiment, we only take the first step. However, when you are listening to multiple landings, you can, for example, you copy the whole basal function and paste on it. So you can see that there are another peaks, another functions on, so it will cause harmonic of the sound. So the frequency will change if you are not.
Okay, so any other question? Okay.
How can you show the frequency, the measurement of frequency? So my question goes to everything. So how would the height of the cup affect your measurement of frequency, the spectrum, your frequency spectrum? Yeah, this one. Yeah. So how would the height or depth of the cup affect your measurement of frequency?
So because the volume of the air particles inside the cup is different, so it will cause the resonance to cause the tune of the frequency to be different.
Okay, so I believe that by changing the height of the height of the cup, the first peak right here caused by actually the membrane vibrating will not change. However, the higher harmonics, which is caused by the air inside the cup, would change because of like the different length, which would cause different harmonics, which will cause like standing waves and other harmonics, so that the higher frequencies would not be the same.
Okay, it's about time to prepare your score. Okay. Okay, so let's show the scores for the reporter. 7, 8, 7, 7, 8. And then let's show the score for the opponent. 8, 8, 7, 8, 7. And then finally the score for the reviewer. 5, 4, 4, 5, 5. Okay, so let's end this stage of the fight.